Okay, how to do ray diagrams. Okay. How to do ray diagrams. First, let's start with lenses. Okay, more specifically, let's look at converging, where your object distance is greater than your focal point. Okay. When we draw these ray diagrams, there's a variety of assumptions that we're making with lenses. This is specifically, we're usually assuming a thin lens. So in other words, the thickness of the lens is pretty small compared to how far your object is and the dimensions of your object. Okay. So, first, we're going to draw our principal axis, just a horizontal line. Somewhere in here, we're going to draw our converging lens. Looks something like this. The main thing, pretty much we're going to treat this lens as if it's just a vertical line. In other words, as the light rays come in, they interact with the lens at the vertical line. In real life, it's not quite like that, but close enough. Okay, so we're just going to make an object. I'm just going to keep it simple. I'm just going to use an arrow. Okay, and let's say the focal point is right here, F. Okay, so when we talk about the focal length, the length is measured from the mirror. So this would be like my focal length right here. And then this would be my object distance from here to here. Right? So my object distance is greater than my focal length. When you do lenses, you're going to draw your focal length on both sides. Technically, this works, most of the problems that you'll see for like SAT2s and stuff assumes that it's a symmetric lens, so then the focal length will be the same on both sides. When you have something like this, the focal length is not necessarily the same on both sides because it's curved, in different ways, different amounts on both sides. So we'll estimate about the same focal length on both sides. Okay. The most important thing about drawing these ray diagrams to figure out where your image is going to show up is your three principal rays. You only need two of them, but let's go through all three. The assumption, or not the assumption, but the way it works out, the first principal ray is your parallel ray. When you have a ray coming straight on, and it can really help to kind of use a ruler or something, but if you want to try and eyeball it, you can. Any ray going straight on, okay, parallel to the principal axis. So this is the principal axis. And then this is one of the principal rays. This is the parallel ray. That ray is going to go straight towards the focal point. Okay, parallel rays go towards the focal point. Then it should happen in reverse, that if I send light through this focal point, afterwards it should go parallel. Okay? So what you can do is, these two principal rays already should give you where the image is going to be. Because it should be where the two rays meet. Your third ray can be a nice check to make sure it makes sense. Okay, so yeah, again, going back, you got the parallel one goes towards the focal point. The one that goes towards the focal point then becomes parallel. Because imagine if this is going in reverse, right? A parallel ray coming this way should go towards the focal point. So it should go it should behave the same both ways, especially for these, assuming it's a symmetric lens. The last one, a light ray that goes through the center of your lens should pass right through, and you should find that it essentially cuts right into where the image is. Okay? If everything were perfect straight lines, for the most part, all three lines should meet up. Okay? Okay, so one of the equations, it's both the lens and mirror equation, is this one, and it is 1 over f equals to 1 over object distance plus 1 over image distance. The hardest part about using this equation relates your focal length to your object distance and your image distance. And the hardest part about using this equation is keeping track of the sign conventions. See, because when you use, when you try and use this equation, for a converging lens, your focal length is a positive number. Your image distance, this is a positive number too. They're both positive numbers. We count them as positive numbers because they're coming out on the other side of your lens. That's important. You'll see where it goes backwards in a second. Okay. Some other things to kind of notice about this equation, and if you can visualize what happens as you pull this image further away or closer in. As you increase your object distance, this fraction gets smaller, right? At the limit where your object is at infinity, your image gets closer and closer to the focal point. And that should make sense, because if your object is almost infinitely far away, all three rays eventually become essentially parallel rays, right? So then it goes in reverse. Oh, sorry, go ahead.
What's the d sub I?
D sub I is the image distance. So image distance is this distance. Yeah. That's the image distance. And then your object distance is like way out here, whatever the...
So is your object distance negative? Because you're saying the other two are positive?
No. So your object distance is always positive.
So everything is positive?
In this case, everything is positive. However, you may notice that your image is inverted, is upside down, which is, you may have heard this plenty of times, that your eyes create an inverted image in the back of your eyes for this reason. You have a converging lens on your eye. Okay? Okay, so in reverse then, imagine I take this from infinity, my object from infinity, the object's at infinity, the image is right at the dot, and as I push it closer and closer and closer, my image goes further and further away, right? At the limit where if my object distance is exactly right on the focal point, this needs to go to infinity, right? So what's going to happen is your image is just going to like keep growing and going further and further away until it's just like there's no image, right? If you put an object right at the focal point, all the light coming from it should go parallel and have no image whatsoever. Okay? So what happens when you flip over? Let's say, now let's look at converging, but your object distance is less than your focal length. Okay, so we're going to draw this again. Here's this line. Principal axis. Here's my lens. Dot, 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 dot. This time I'm going to exaggerate. I'm going to exaggerate my focal length. I'm going to put it over here. And now I'm going to put my object really close in.
Wait, so the one we did beforehand was diverging?
This is converging. They're both converging lenses. It's the same thing, but now what I'm going to do is I'm going to put my object inside between the focal length and the lens. Okay, so here's the focal length. I'm going to try and repeat that location. So what is that, like this much? Yeah, if you want to eyeball it, that's fine, but I'm trying to keep it super exact for the demonstration here. Okay? Okay. So we're going to do a very similar thing. Parallel ray coming straight on should go towards the focal point. But this time, I can't really draw a line towards this focal point because that's like going backwards, right? So instead, what I'm going to try and do is imagine that the whole point of these two principal rays, the one that's parallel going towards the focal point and the one that's going towards the focal point and becomes parallel, is that they're kind of like symmetric traces of each other. Does that make sense? This is parallel, goes towards focal point. This is parallel, goes towards focal point, right? If you're coming in from the other side, the light ray should behave the same way. It should follow the same path. So since I can't go towards this focal point, I'm going to try and imagine if there was some light ray that was parallel on this side that had to go towards the focal point, where would that come from? Essentially what I'm going to do is I'm going to trace backwards through my focal point this way. Does that make sense? So then this light ray should go parallel. Right? Because if it was coming in parallel from this side, it should converge towards this focal point. And so what I have is on the left side, parallel to focal point, from the right-hand side, parallel to focal point. What you may notice now is that on the right-hand side, where these two light rays are going, they are diverging light rays. Okay, so whenever you have diverging light rays, what that means is it's going to be a virtual image, and you want to trace back where it appears those light rays are coming from. So actually I'm going to take this line, and I'm going to trace it back, and I'm going to take this light ray and I'm going to trace it back. Okay, so it will appear as if these two light rays are coming from this spot. Let me use a different color pen to indicate the image. Does that make sense? So in other words, if I take this giant converging lens, okay, and it has some focal point right here, and I put an object right here, and I'm trying to look at the object right here, it will look as if it is bigger and further back than where it actually is. Okay? If you don't trust me, you can pass it around and try and play around with that. But put something on the other side of it. The closer it is, the bigger it will look, and the placement of it is weird, especially if you're looking at this and then just look over on the other side, like look at the real place. It doesn't look like where it's actually is. Yeah.
So you said that's a virtual image. Is the image in the converging diagram with
This one?
Yeah, is that one a virtual image?
This is a real image because the light actually converges here.
Oh, okay.
This is virtual image because there's no light actually coming from this spot. Right? And then you can check with your third point, your third line should be, if I go from here towards the center, it should cut right through. And if I trace that backwards, it's kind of close. I mean, it's pretty close. It's pretty close. If you had if you're very, very careful about all your lines. it should work out. Right? All three should look like they're coming from this spot. Okay, so let's look at this math a little bit. Why is it that this is creating, in other words, what you should find is that the image distance is negative. Let's look at the math of that. If the distance, the object distance is less than f, that means this is a bigger number than this fraction, right? If DO is smaller than f, this fraction is bigger than this fraction. So when you take the difference and solve for DI, this ends up being a negative number. And so mathematically it still works out. There is one other equation that comes up, and it's called the magnification. The magnification equation. Someone forgets. Is the negative image distance divided by object distance. Okay. So what is magnification? Magnification is basically how much, by what factor does your image get bigger or smaller, right? So, you can find that your image, notice the negative. The negative means that it's going to flip. If this is a negative number, it's an inverted image. If this becomes a positive number, then it's a upright image. One thing that tells you then is that in order to ever have an upright image, one of these has to be negative. It's going to be your image distance, meaning that only virtual images are upright and all real images are always inverted. Yep.
So what does the M stand for?
M is for magnification. Yeah, I mean, there's a lot of different kind of deductions you can make from these equations. You don't have to memorize them, but if you can get familiar with them, it can really help do kind of these, check your own answer or do multiple choice questions, really fast conceptual questions. Okay, any questions about this? This is converging lenses. So, let's lastly look at diverging lenses. For a diverging lens, yeah, just pass it that way. For a diverging lens, it doesn't really matter the location of the object to the focal length. Yeah.
So is there a specific diagram for magnification?
So magnification, then it's just the ratio of image distance to object distance. So you can see that whenever it's closer, it's going to be smaller. When it's further, it's going to be bigger. Yeah. Okay. So for a diverging lens, we will sketch it like this. Draw our principal axis again. This time we're going to kind of sketch the diverging lens like this. Okay, so it's concave on both sides. You can say that these are convex on both sides. Convex points bulges out, concave shrinks in. Okay, so when we look at a diverging lens, our focal point is negative. Okay, our focal point's going to be negative. What that means is, okay, let's say I have an object over here. Draw my arrow. And let's say the focal length is right here, and the mirror of it, I'm just kind of eyeballing over here. Okay. So now, instead of bending the light towards the focal point on the right-hand side, our focal point is like on the other side. So the light is gonna kind of, so parallel ray coming along like this, instead of bending towards the focal point, it's gonna bend away. It's diverging. it's gonna divert this light as if it was coming from this spot. Oops. Does that make sense? How like the negative focal point is a way of mathematically representing the divergingness. Okay, it's, you can imagine like well, I'll wait a second before I kind of throw this out there. But you can kind of think of it like this, okay? A flat lens, which is just like a pane of glass, has no focal length. The focal length is infinity. It just lets light pass straight through. The more you round it, okay, the closer you pull that focal point in. The more you make it concave and start bending it the other way, it's like the focal point is coming from the other side, kind of like a hyperbola, you know what I mean? Like it's switching sides, right? So as you're bending or curving the two sides of your lens from concave to convex, you're like shifting that focal point around, right? So we've shifted the focal point over here. Okay. So this one is it's a little tricky. So instead of trying to draw the line through the focal point this time, like to make it become a parallel ray, it doesn't behave like that, right? Because parallel rays don't go towards the focal point, they go away. So this time we're going to use the other principal ray, the one that goes through the center. That's the easier one to use. That's going to go like this. The principal ray that goes through the center always just goes straight through. Okay, so you can see where they cross, where it appears as if they're coming from. These are diverging, so you trace them back. And so this is your image. It's virtual, it's upright, it's closer, so it's smaller. And generally speaking, that's what, well, for a diverging lens, this will always be a virtual image. If you bring this closer in, okay, well, I guess we can just kind of look at the equation. If your object distance is equal to your focal length, your image distance should be 0. So once again, your image should kind of just go away as you get towards here. And then it will come back around from the other side. It's kind of weird. Or, no, hold on, let me think about that. I can't remember what the generalization of that is actually. But your image distance, your image is going to be like this. It's really hard to draw that third ray. I can't remember. Just use these two rays. These are the easier ones to use when you're talking about diverging lens. Okay, so
This is for Z naught is greater than it.
this is, well,
Or does it not?
it doesn't particularly matter for diverging lenses. For diverging lenses, you always get a virtual image. It's always upright. The size of it, though, you just have to plug stuff in here. So again, what can be tricky here is, in the case of a diverging lens, you have a negative focal point. This becomes a negative number. And so all the other calculations will need to adjust accordingly. Your object distance is still positive, but what you should find is then that your image distance is also a negative number. It's on this side. The light's not actually converging, on the other side. Yep.
Does this apply like even if the object is outside of the focal point and inside of the focal point?
Yeah, it should work either way. It should work either way.
So anything with the virtual image has a negative distance.
Has a negative. Yeah. Another way you can kind of think of a virtual image is if you have a situation where there's a virtual image, you can't put a piece of paper on the other side of the glass and ever see what that image is. It will never create an image. When you have this case where it's a real image, you can actually put a piece of paper there, and whatever it looks like here will actually look like right here. I know that may seem kind of weird because we're so used to seeing things with our eyes and not actually having the light build up somewhere, but we're gonna do that in the lab between today and Tuesday. Okay. Okay. Tell you what, I'd rather you guys get a chance to start seeing this. So we'll just do lenses today, and then we'll do mirrors on Tuesday. So I'm gonna give you the lab. The lab goes through both lenses and mirrors. I just want you to try and do the lens part today. Let me show you the equipment a little bit. Stop recording.